All for coming. My name is Alberto Marín, and I'm going to give you a brief update of the activities that I have done this year in my PhD activities. So the name of my PhD topic is a two-dimensional model of wall interaction in a Hall effect thruster discharge, and my supervisors are Eduardo Aedo and Adrián Domínguez, which is now in Málaga. So I have decided to structure my presentation in these different sections. So first I'm going to do a brief introduction of the problem. I'm going to tell a little bit the motivation. I will go through the methodology, but very fast. And I will show some partial results of 2D simulations that I have done, very briefly. And then I will conclude with some summary and future work of the activities that I'm going to do. So let's start with the introduction. As my colleagues have mentioned before, especially Enrique, Hall effect thrusters are currently leading the sector of electric propulsions because it's a mature technology that has been used over the last 60 years probably to thrust spacecraft in space. And then we have different type of populations that do different things. So for example, the neutrals are injected through the anode backplate and they get ionized in the channel. These ions get accelerated downstream and are those that generate the thrust. And the electrons are generated through this cathode, and they are split into beams. So one of the beams is going towards the downstream to neutralize the ions that are going down, and some part of the electrons are coming inside the channel and are the ones that are actually ionizing the neutrals and generating the ions that we need to make the thruster work. But as Enrique has presented before, although this is a mature technology, not everything is known. And there are two main problems that are still open, which are plasma wall interaction and anomalous transport. So since he has been talking about anomalous electron transport, I am going to focus on plasma wall interaction, which is the topic of my thesis. So the main goal of this thesis is a theoretical study of plasma wall interaction, and I'm going to do it mainly through numerical simulations. Why do we even care about plasma wall interaction? Well, because it's very important. It is responsible for energy losses, ion recombination, wall material erosion, and some other authors even claim that it is generating part of the anomalous transport that we also see. So very important things happening here. So now, how do we tackle this problem? How are we going to analyze this plasma inside the Hall effect channel? Well, it is required to solve the plasma dynamics inside the channel, and we figured out that this is a very weakly collisional plasma. So there is no thermodynamic equilibrium, which implies that we require a full characterization of the species velocity distribution function. So this implies that we need a kinetic model for the plasma. But this is computationally expensive, okay? We have to solve length scales of the order of the by length, time scales of the inverse plasma frequency, and you have different species with very different dynamics, which in the end make the simulations very lengthy. So what do people have done? This is the governing equation for the plasma, which is the Boltzmann equation, which in this here you have this f, which is the velocity distribution function, which is the unknown that we want to solve, okay? But what happens? That this is very difficult because this velocity distribution function represents the number of particles in a given region of space with a given velocity. So in general, this f variable depends on the 3D position and the 3D velocity. So it depends in 6 dimensions. Plus, at the time, it makes 7-dimensional. So it's very difficult to solve this problem. So people say, okay, let's don't solve this directly. Let's take some integrals and let's solve for some macroscopic transport equations. And this is what we typically known as fluid models. But we know that these don't work. They don't work because of what? Because we have mentioned before that the discharge is weakly collisional. So even if we don't like this equation, we have to solve it. This is the life. So there are two different methods to do it. This is the fully kinetic, which is just taking this equation, discretize it with whatever method you like, maybe finding differences, finding volumes, and just solve it as it is. And then you have the particle method, which is the peak, which in the end is the same but in a different way. So you discretize this velocity distribution function in terms of particles, and then you move these particles in your domain according to the forces acting on those particles, which is basically a statistical representation of this velocity distribution function. So now let's talk a little bit on the details of this method, which make the simulations a little bit time consuming, and why it is that. Well, we have some limitation in time step and cell size, which are related with this plasma frequency and divide length, and we also have a third condition, which is regarding the CFL, which is a condition for getting accurate solutions of the plasma discharge. Then we have different time scales of the different species in the plasma. So we have here that the electrons are much faster than the ions, and these are much faster than the neutrals. And in the end, there is roughly 2 orders of magnitude between the dynamics of one and the other. So in the end, it is very challenging to compute the solution of this plasma as it is. So we need several techniques to make the simulation go fast enough so that we can get solutions in a reasonable time. So we make use of parallel computing in order to get simulations in some realistic times, and we also use some acceleration techniques in which we reduce part of the physics of the problem and we make some assumptions, and with that we can also reduce the computational cost of the simulation. So in the first place, we can say, okay, we are mainly interested in the dynamics of ions and electrons. So let's forget about neutrals for the moment, and with that we have a speed up of 2 orders of magnitude, which is not too bad. And then we also found out that these 2 numerical constraints are linked with this parameter over here, which is this epsilon. So if somehow we can use a larger value of the vacuum permittivity, this epsilon, we can make the simulations much faster. Okay? But someone will say, okay, this is like cheating. You are changing the physics to make the simulation faster. So let's see how this compares. So I have shown here 3 simulations. This is the highest fidelity simulations, and these others are less fidelity simulations. The first thing that we can see is that mainly the 3 of them follow the same trends, although there are some differences, and especially the biggest difference you can find between the green and the red and black, okay? Because the red and the black ones are almost identical in all senses. But the important thing I want to highlight here are the simulation times. Like, the highest fidelity one takes 5 weeks to simulate, but this red one, which is almost identical to the previous one, it already takes 5 days. And this green simulation, which is lower fidelity, it takes 1 day. So in the end, this trick that we have done in the physics, it affects sometimes the results, but as long as you are in a reasonable range, like if you are over here, you can get reasonable solutions with an acceleration, a significant acceleration in the simulation. All these results and more are in this paper that we have recently published in this February. So if you want to know more, I refer you to that. And now let's talk a little bit about the 2D simulations of a Hall effect transistor, which is in the end the final goal of this thesis. So the first thing I want to mention is why we do 2D axial radial simulations and we don't do other things. So we could have gone to 1D models because these are affordable, but you have to make strong assumptions in order to compensate with the 2 missing directions. So this is probably not good enough. Then you can also go to 3D models and solve everything. So this potentially captures all the physics of the discharge, but the problem is that they are too computationally expensive, even with the acceleration techniques that I have mentioned before. And then we have 2D models. And we think that this is a good compromise because it contains the axial direction, which is the main direction of the discharge, and we also can capture with the radial direction some wall effects, which is the main goal of the thesis. We still are missing something, which is the azimuthal direction, and we need to use a phenomenological model for anomalous transport. In previous presentations of this code, I was presenting some simplified versions of these simulations, but they were missing some important physics. For example, in previous simulations, we saw that there was an important change between radial and oblique magnetic field topology. We also included cylindrical geometry effects because, of course, this transistor is not planar, it's annular, and we need better descriptions for the electron-neutral collisions, which also Matteo is using for his plume simulation. So this is also an improvement for the model itself, that it is not only valid for this, but for other things. So these are the simulation results, which show the expected trends in all the macroscopic magnitude of interest. So we have here the maximum in the electric potential close to the anode, and this decays towards the exit, and it also decays towards the walls. You have here the electron temperature map, which is close to it reaches its maximum at the thruster exit. You have an electron density map, which is pretty much the one that one should expect, and the non-neutrality map, which shows that most of the plasma is quasi-neutral, and you have small non-neutral regions very close to the walls, which is the expected trend, because there you will have non-neutral device sheets. But should we trust these results? Are these results correct, or are we violating any other physical law? So let's check. So the objective of these simulations is analyzing the steady state of these thrusters. So the first thing that we want to make sure is that our results are stationary. And after some chaotic transient, I would say, we converge to a pretty much constant solution with some noise, which is typically inherent of the peak codes, which always have some noise. Then, what else can we check? Well, we can.
Alberto, you need to finish, okay? As soon as possible.
So we also have to conserve some other magnitudes, such as mass flow and discharge current, which is also conserved. And we also made some comparison between different domain sizes, because the plume doesn't end here. This is a finite domain, but in reality it expands to infinity. So we have changed the domain with different sizes, and we said that the results inside the channel, which is like this, in this part, do not change significantly with the domain size. So we are quite happy with these results, and we're going to consolidate this for the IEPC conference, and I have to focus on the thesis writing, which I should be finishing very soon. So these are some conferences I have attended and some contributions, and these are some more journal papers, and this is all from my side. And if you have any questions, I will be happy to take it.